To complete our picture on orthogonal subspaces, we have to talk about orthogonal complements. So what is an orthogonal complement? Let's write that definition. So the orthogonal complement of a vector space V is the space V perp, so V perpendicular, but it's pronounced V perp, consisting of all vectors perpendicular to V. Now, it's not, I don't want to be too precise, but we should, when I'm defining these V and V complement or V perpendicular, the perpendicular complement, I mean that these are subspaces of some overarching space. So for example, if we take V in Rn, then we're talking about its perpendicular complement also in Rn. So this is not just some spaces, they can't be any spaces. Now, how can we tell whether so we have this definition, great, but how can we tell that two vector spaces are orthogonal complements of each other? So how can we tell that two subspaces of the same vector space are orthogonal complements? By the way, from the definition of an orthogonal complement, if V perp is the orthogonal complement of V, then V is the orthogonal complement of V perp. Or if you do perp, you go back to V, right? It's kind of almost intuitively clear, but I just wanted to put it out there. That's why we say orthogonal complements. We don't want to pick on any one vector space. Okay, so let's answer this question. How can we tell that two subspaces of the same vector space are orthogonal complements? Well, two things. First, the two subspaces need to be orthogonal. Right? So if you have a basis for V and a basis for your potential V perp or W, whatever we call it, we can check if the two subspaces are orthogonal. But when are they orthogonal complements? Well, if the dimensions add up to the dimension of the space. So if the dimensions add up to the dimension of the space that contains them. What I mean by that is, let's focus here. So Rn, this big vector space, is n-dimensional, right? So if we take a basis for Rn, it needs to consist of n linearly independent vectors. It cannot have more, it cannot have less. That's how we define dimension. So if this vector v has dimension k, and this other vector space, which is orthogonal to v, has dimension n minus k, so if here the dimension of v is k, and the dimension of this potential, the potential complement is n minus k, then we know that the two must be complements because there cannot be anything else. So the dimensions do the trick. Now, with this definition, with this understanding of orthogonal complements, we are ready to state the second part of the fundamental theorem of linear algebra. So the fundamental theorem of linear algebra, part 2. Part 1, if you recall, talked about the dimensions. Now part 2 tells us a little bit more. It tells us that the row space of A is the orthogonal complement of, sorry, I said the row space, I need a T there, of the null space of A, and all of this is happening in Rn. And the column space of A is the orthogonal complement of the left null space. And this is happening in Rm, right? So the column space and the left null space completely put together completely describe Rm. And similarly, the row space and the null space completely describe Rn, meaning I can take a basis for the row space and a basis for the null space, and that will give me a basis for the entire space Rn. And I can take a basis for the column space and a basis for the left null space to get a basis for the entire space Rm. Why would you ever want to do that? Well, the reason is that A acts as a map between these spaces. So let's repeat the picture that we have. So here we have the rows of A. And we know that the dimension here is the rank R. All this picture is happening in Rn. Then orthogonal to it is the null space. So these are all vectors orthogonal to the rows. And we know that the dimension of that space is n minus r, the number of free columns. These two intersect. The only thing they have in common is the zero vector, and they are at 90-degree angles. Now, when I apply the matrix A to the rows of A, and by apply I mean when I carry out matrix multiplication, I come to the columns of A. I get a combination of the columns of A. And here I have all vectors orthogonal to the columns of A. The dimension of the columns, or the column space, is R, and the dimension of all vectors which are orthogonal to the columns is M minus R, because this whole picture is happening in Rm. And now you can take a vector from the row space, and you can take a vector from the null space, put them together. So you have X row, X null space. Together, they give you another vector in Rn. So any general vector in Rn would be the sum of a vector in the row space and a vector in the null space. You apply A to them, to that sum. So if you apply an A to any vector in Rn, you are going to get a vector B in the column space of A. And if you only take a vector in the null space, you are going to get to 0, right? Because this is 0, this is B. So you see that A transforms Rn into Rm. This is what's called a linear transformation. And it's a formal subject to be studied in linear algebra, but we're not going to do that in this course. So every matrix represents a linear transformation from the space Rn to the space Rm. And what is very important is to note that we can completely get this column space of A by just applying A on the rows. So if I take a basis for the row space and I multiply A by those rows, I'm going to completely get a basis for the column space of A. I'm going to describe the column space completely. And if you see, I cannot describe the left null space from A, but I can describe it as the space consisting of all vectors which are orthogonal to the columns of A. And we know how to find a basis for that space. So the reason we want to split Rn and Rm into these orthogonal complements is because we can see how the map A, or the matrix A, maps one space into the other, and how the bases actually also get mapped. Now all of this gets mapped to 0, and you obtain this by looking at orthogonality with that vector space, and you can look at the null space by orthogonality with the row space. All right, now let's use all of this to answer the following example. Let's look at an example of how we can use this matrix picture in a more standard way. So let V equal span of the vectors 1, 2, 3, 4, and 1, negative 1, 1, negative 1, right? So clearly these two vectors are linearly independent. Clearly this V is a subspace in R4 because the vectors in the basis that is given here have 4 components. Now, I will ask the question, find a basis for the orthogonal complement of V. So how can I find, or how can I describe the orthogonal complement of a vector space that happens to be in R4? We are mostly interested in vector spaces that are column vectors, consisting of real numbers. All these things are also true for complex numbers. But as I noted, as we mentioned when we talked about vector spaces and bases, you could have a vector space of matrices, you could have a vector space of functions, and all the algorithms that we have in here, how they work for finding their complements are not difficult, but we're just not going to discuss them in this class. So we're just going to focus on vector spaces consisting of column vectors. So if I'm given such a vector space, then I want to find a basis for the orthogonal complement of this vector space. How can I do that? Well, I'm not given a matrix, but that doesn't mean I can't make a matrix. Now, if I, the question is, do I put these vectors to be the rows of a matrix, or do I put them to be the columns of a matrix? Well, I can kind of do either, but then I want to know how to find the complement of what these vectors represent. So if I use, if we take A to be 1, 2, 3, 4, 1, negative 1, 1, negative 1. So what I'm doing here is I am saying let V equal the row space of A. So I'm taking a matrix A whose row space is this vector space V, this subspace V. I can do that. I can choose such a matrix anytime that works for me, right? I can choose that matrix, no problem. Now, from the fundamental theorem of linear algebra, part 2, we know that the orthogonal complement, so if V is the row space of A, then the orthogonal complement is going to be the orthogonal complement of the row space, and the orthogonal complement of the row space is the null space. So ultimately, this pursuit for a basis for V perp is the same as find the null space of A. If I make A to be the matrix whose rows are the vectors that are given in the basis of V. So how do we do this? Well, as I said, find a null space. So we will reduce the matrix. It's just R2 minus R1 into R2. We will get 1, 2, 3, 4, and then 0. Negative 1 minus 2 will be negative 3. 1 minus 3 will be negative 2. And negative 1 minus 4 will be negative 5. Perhaps these are not the prettiest numbers I've ever chosen, but we can still work with this. So we see that the pivots are 1 and negative 3. This is, by the way, the matrix U, the upper triangular, the row echelon form, but not the reduced row echelon form. I can work with this as well. The math would have perhaps been a little bit easier if I had switched the two rows of A, which I could have done, and I would have gotten the same null space because changing the two rows does not change the row space. But anyway, the free variables are x3 and x4. How do I find special solutions? Well, I'm going to set x3 to be 1 and x4 to be 0 for the first solution. From the second equation, so I'm going to get an x with the last components being 1 and 0. Then using this, I want to make sure that the second row of U is orthogonal to whatever vector I'm going to put here. Or I'm just trying to find, just using the equation that this row represents, which is negative 3x2 minus 2x3 minus 5x4 equals 0. Now x4 is 0 itself, x3 is 1. So what we have is 3x2 minus 2 is 0, or negative 3x2 equals 2. And from here, x2 equals negative 2/3. So we have x2 is negative 2/3. And then from the first row, we need to find what x1 must be. So the first equation here represents x1 plus 2x2 plus 3x3 plus 4x4 equals 0. x4 is 0, x3 is 1, x2 is negative 2/3. So what we have here is x1 minus 4/3 plus 3 is 0. And negative 4/3 is with added, you can add 9/3 there. You would have 5/3. Going on the other side, you get x1 equals negative 5/3. So we have negative 5/3 here. That's the first special solution. The second special solution will have 1 and 0. So that corresponds to x3 being 0 and x4 being 1. So we repeat the same process. We're going to have negative 5/3 here. And what should be the first component? I have to write this down. I'm not that smart. So I'm going to have x1 plus 2x2 plus 3x3 plus 4x4 is 0. Now this is 1. x3 is 0. x2 is negative 5/3. So we get x1 minus 10/3 plus 4 is 0. 4 is 12/3. So we have x1 equals negative 2/3. So negative 2/3. I may have made computational errors. Please double check my work. But if this is to be true, we just have to check that the dot product of this vector with the first row is 0 and this vector with the second row is 0. Similarly here with the first row and with the second row. And this is how we can get, and now we can get a basis for VPerp. So VPerp is span of these two special solutions, negative 5/3, negative 2/3, 1, 0, negative 2/3, negative 5/3, 0, 1. So this is what we do if we want to find if we put these two vectors as the rows of a matrix, then we find the null space. Now, what if we wanted to solve this problem using the columns of A? So if we wanted to realize V as the column space of a matrix rather than the row space. So I'm just gonna put that matrix there, put that vector there. So we could very well take a matrix A, this is different from the previous one, where we put these two columns as the columns of A. All right. Well, now what we've done is we've said that V equals the column space of A. Well, then from the fundamental theorem of linear algebra part 2, VPerp must be the left null space of A. So this is a matter of preference. Do we prefer to find the null space of a matrix, or do we want to find the left null space of a matrix? So to find the left null space here, we see that we know that the rank is only 2 because these two vectors, the two columns, are linearly independent. So we know that 2 rows will be linearly independent. And the way to find the left null space, this is a bit of review, but it doesn't hurt to review finding these processes. So we start with the matrix A. Our goal is to eliminate, to get rows of 0. And what we're going to do to define the left null space is we're going to apply those operations on some vector b1, b2, b3, b4. So the first elimination step is with the first pivot. And it says R2 minus 2R1 into R2. R3 minus 3R1 into R3. R4 minus 4R1 into R4. We get 1, 1, B1. Then 0, negative 3, B2 minus 2B1. Then we get 0, and then 1 minus 3 is a negative 2. Then B3 minus 3B1. And 0 minus 5, B4 minus 4B1. And now the fractions will come. We need to use this pivot to reduce underneath it. The operations, so since all the signs are the same, we're going to be subtracting. So we will have R3 minus 2/3 R2 into R3, and R4 minus 5/3 R2 into R4. We get 1, 1, B1, 0, negative 3, B2 minus 2B1. And then we know we get zeros here. And we just have to take our time computing the right-hand sides. So I will write on the side. So I have, for the third row, I have B3 minus 3B1 minus 2/3 of B2 minus 2B1. So that equals B3 minus 2/3 B2. And then I have negative 3 here, negative 3B1. And then negative 2/3 times negative 2, that becomes positive 4/3. So I have plus 4/3 minus 3, B1. And that is, there is a negative there because 3 is 9/3. So really this reduces to negative 5/3. So we get B3 minus 2/3 B2 minus 5/3 B1, or there. Now I will erase this because I need that space. So for the last equation, we have B4 minus 4B1, so that comes from R4, and then minus 5/3 B2 minus 2B1 equals B4 minus 5/3 B2. And now I have to group B1. So I have plus 10/3 minus 4B1. 4 is 12/3. So this whole thing is negative 2/3. And I get here B4 minus 5/3 B2 minus 2/3 B1. And now, where is the left null space? So the left null space comes from these two equations, which must be 0, right? This answers the question on find conditions on the components of the vector b1, b2, b3, b4 that solve ax equals b, right? So then the vector the vector b must have, its components must satisfy these two equations to have a solution. So how do you find the vectors then for the basis of the left null space? So now the left null space, which is V perp, is span of. Now, from this first equation, we write first the coefficients for before b1, then before b2, before b3, and before b4. Since there is no b4, it means b4 is a 0. So I know that b4 is 0. b1 has negative 5/3. b2 is multiplied by negative 2/3. b3 by a 1. And then the next equation, you see no b3 shows up and b4 has a 1. So I have this here. b1 has a negative 2/3 in front of it, and b2 has negative 5/3. So I found the same vectors, except that this second case I think was much harder because I had to do a lot of elimination, whereas before the elimination wasn't much, but then it's a matter of preference, I suppose. Do you want to work with numbers or do you want to work with letters? And I suspect most of you prefer the first method, myself included, but I just wanted to show you that you can really use both cases, except you have to be careful. If you put the vectors that are in the basis as the columns of A, then you have to use the fact that the orthogonal complement of the column space is the left null space. So the question is, do you want to find the left null space of a matrix, or do you prefer to find the null space of a matrix? The bottom line here is that as long as a vector space consists of column vectors, we can always realize that space as a column space or a row space of a matrix. Literally put those vectors to be the rows or the columns of your matrix A, and then all of a sudden your V becomes one of the 4 fundamental subspaces that we've studied. We know how to find their orthogonal complements. We know how to find, how to make sure that we have a basis and not nothing more. So in other words, we want to make sure that we have linear independence. Of course, here it's very easy to see that we have linear independence because we only have 2 vectors. But what if we have 4 or 5 or 6 and the vectors have more components? Now, we've sort of, the biggest matrix we've worked with is 4 by 5. But these operations are very easy for computers. So realizing such vector spaces as matrices means that we can teach a computer how to implement all of these procedures and compute for us column spaces, null spaces, left null spaces, row spaces, and all the 4 fundamental subspaces, which give us a lot of information about the types of systems that we have. So we can, if we have some vector space described by a collection of vectors, then we can check whether we have a basis by sticking those vectors as the columns or rows of a matrix and then just reducing. So if we take the column vectors that would be given here and place them as the rows, as we carry out elimination, so the advantage of placing them as rows rather than as columns is that V continues to be the span of these vectors as well. So we have another basis for the same space. If we have many more rows and we carry out elimination by taking the pivot rows, we have another basis. But of course, you can do the same with the columns. Of course, the column space of the matrix A is not the same as the column space of this matrix U, but because both of these columns have pivots, we know that we already had a basis with those columns, that they are linearly independent. So we have lots of freedom, and the realizing vector spaces of column vectors as one of the four fundamental subspaces of a matrix just gives us algorithms that we can use with software that already exists. All right, that's all for today.